Hola, soy Dora the Chemist. Welcome to my lab. Today I'll be teaching you all about spectroscopy. Isn't that when they put a camera in your guts? Oh, how could I forget? This is my friend Boots. And no, that's a colonoscopy. Spectroscopy is the study of how matter absorbs, emits, or scatters light. Ooh, that sounds cooler and less painful. How does it work? Well, come inside my lab and I'll show you. Since spectroscopy is all about light, the first thing we should do is understand how light and matter interact. Here, let me show you how this works on this chalkboard. Okay, sick. It all starts with white light. White light is actually made of all colors of the rainbow, as you can see here. Every color has different wavelength. Reds and oranges are the longest, and blues and violets are the shortest. Matter absorbs light, but only in certain wavelengths or colors. So a yellow shirt absorbs yellow light? Actually, Boots, it's the opposite. Whatever light isn't absorbed is transmitted, and that's what we see. So the light observed is complementary to the light absorbed. A yellow shirt absorbs all colors from the white except yellow. Yellow light gets transmitted, so the shirt appears yellow to our eyes. Oh, that makes sense. Mathematically, we can say transmittance is the ratio P divided by P naught. Now let's say we had a test tube and we shined light at it at an initial intensity of P naught. Then some of the light will be absorbed and whatever comes out is at intensity P. Transmittance is this ratio of what comes out divided by what goes in. How do we find absorbance? Well, I was just getting to that. Absorbance is the negative logarithm of transmittance. Oh, that looks like complicated math. Not really. The negative sign means that there's an inverse relationship. Think about it. If more light is absorbed, then there has to be less that was transmitted. The logarithm tells us that when all the light is transmitted, as in P equals P naught, then transmittance is 1, and so absorbance is 0. It also means when transmittance increases 10 times, absorbance goes down by 1. 1 what? What's the unit? Actually, absorbance has no units. It's just a relative scaling. Okay, I think I get it now. Great. Well, now we can get to the fun part. Here we are. This machine is a spectrometer. It separates wavelengths of light and detects how much each wavelength is absorbed. To take an absorption spectrum of the solution, we would first pipette it into this small rectangular prism called a cuvette. Its standard width is 1 centimeter. Now, before we ran this cuvette through, we actually filled one with just water, which is called a blank. We took it so that we could get rid of any noise or any absorption that wasn't due to the solution itself. Now, even when we're putting this one in, we have to wipe it down with Kim wipes to get rid of any fingerprints. Otherwise, they could absorb light and mess up the data. As you can tell, this is quite an exact science. Then we put our cuvette in the machine and it does all the work for us. At the end, we get a graph which will come up on the LabQuest machine that we have right over here. Let's take a look. See, right on this graph, we have all the absorbances at the different wavelengths that we took it at. You can also see the colors that each wavelength corresponds to. On the right side, you'll see that they gave us the maximum wavelength and absorbance. So that was really this point right here. It was at a wavelength of 497 nanometers and the absorbance was 0.866. Wow, that's neat. Do chemists actually use this stuff? For sure. Analytical chemistry is an important branch of chemistry, and spectroscopy has several applications within it. Let me show you how this data can be used. Alright, so this is Beer-Lambert law. A is absorbance, which we know about. C is concentration in moles per liter, and L is path length. In our case, the path length is 1 centimeter, the width of the cuvette. The funky letter, epsilon, is a constant called the molar attenuation coefficient, or molar absorptivity of the substance, in units of 1 divided by a molar times centimeter. Let's say we wanted to find out what epsilon is. We could prepare dilutions of our solution and take the absorbance of each of them at the same wavelength. Our best bet would be to use the wavelength with the highest absorbance. Looking back to our LabQuest machine, that was 497 nanometers. Then we can graph absorbance versus concentration, like so. This is called a calibration curve, since we're graphing the response based on concentration of a substance. The slope here is epsilon times L, path length, but we know L is 1, so the slope is just epsilon. Gee, all that information from some trials on a spectrometer? That's not even all. What? How much more is there? There's so much more. What we did is analytical spectroscopy. We used visible light from about 400 to 700 nanometers, but you can use any electromagnetic radiation. See, this is the whole spectrum. Visible light falls right in the middle. See how small what we used was? There's a whole variety of different types of radiation we can use. One of them is radio waves. And with that, you can do nuclear magnetic resonance spectroscopy, which is also known as NMR for short. Radio waves can cause a change in nuclear spin and tell us a lot about hydrogen atoms. That's why it's commonly used for organic compounds. This is a nuclear magnetic resonance spectrum of ethanol. We have signal intensity on the y-axis and chemical shift on the x-axis. The peaks tell us about the hydrogens. Hey, why does this one look different? Well, the hydrogen on the OH group is not coupling with the other hydrogen atoms, so it appears as a singlet. You can kind of tell by matching it with the diagram at the top. The CH3 and CH2 hydrogens are coupling with each other, which results in a triplet, right here beside me, and a quartet to the left of you. Next up, we have infrared spectroscopy, which is at a higher energy and lower wavelength than radio waves. Now with this, we can find out about different bonds within a molecule, because infrared rays can cause bonds to stretch, compress, and vibrate. Alright Boots, now this is an infrared spectrum of methylaniline, which you can see right up here. As you can tell, each peak shows you a bit about the types of bonds within the molecule. They've all been labeled here, and you can see that every single bond always has the same transmittance. No matter what molecule you use, you can identify what kind of bonds are in there. Next up is UV vis spectroscopy. We did part of this. We used visible light, but you can also use UV. This type of spectroscopy can tell us about the valence electrons of an atom. Last but not least, we have photoelectron spectroscopy, or PES, that uses X-rays. Now this is a bit higher energy than visible or UV light, and so it can tell us about more than just valence electrons. It can tell us about core electrons and the number of orbitals in an atom. Alright, to end things off, this is a photoelectric spectrum. As you can see here, there's a bunch of different peaks, and we've plotted the intensity against the energy it takes to eject an electron. So the height of the bars tell you about how many electrons are in each peak. As you can see, the one on the complete right is double the height, as you can see here. So there's twice the amount of electrons in this one. Now if we see here, there's two that are very close in energy and one that's further away. We can tell that this first one then is the 1s orbital, and it has 2 electrons. Then this is the 2s with another 2 electrons, so at the same height. Then the last one here is the 2p orbital. Now since it's double the height, it must have 2 times 2, which is 4 electrons. So we add this all up, 2 plus 2 plus 4. That gives us 8 electrons. This must be oxygen. Whoa, you found out what it is just by looking at this graph. Yep, that's the whole point of it. Well, Boots, that just about wraps up our day at the lab. Hope you learned a lot about spectroscopy. Yeah, I definitely did. I never knew there were so many different ways you could use it. Yeah, for sure. And we barely even touched the surface. There's flame spectroscopy, mass spectroscopy, so many things we haven't even talked about. Wow, that's awesome. I hope to learn all that from you a different day. Yeah, for sure. For now, see you all later, and thanks for watching.